Okay, so we're going to do planes in space. Last time we did lines in space. And remember, a line in space isn't the same as a line in the plane because you need 3 equations all wrapped up in one big set just to describe one line in space. But what about a plane in space? We're going to look at, you only need 1 equation for that, thankfully. But before we do the planes in space, let's do some review. So let's see if you were really there on Friday's lecture, or maybe not. I don't know. It's been a long weekend. So what 2 pieces of information can you recall that you needed to come up with your parametric equations for your line? There were 2 pieces of info. Does anybody remember what those might be? So you're trying to get your parametric equations for your line, which have this look to it. You got x, y, and z, and you have x1 plus at, y1 plus bt, z1 plus ct. This is what it looked like. Does anybody remember the 2 pieces of info we need? If not,
Yes.
it's okay.
A vector.
Okay, a vector. A vector what? Just any old vector or a particular vector?
V vector.
Direction vector.
Direction vector. And what was special about the direction vector? It should be, if you were drawing things, what relationship does the direction vector have with your line? Let's say, let's say here's your line in space. Whoop, there it is, this pink thing. What relationship should your direction vector have with that line?
Parallel.
Good. So it should be parallel. So I'll just make it in standard position down here. There's your V. It's got to be parallel, and the components are A, B, and C. It's what we call the direction numbers. Now you need one other piece of information here besides your direction vector for that line to get your parametric equations for your line. Does anybody know, besides Lizette, what is the other thing you need?
A point on the line.
Good.
Yeah.
A point on the line. Very good. Fantastic, Kimberly. That's awesome. So you got to have a point, any point on the line. So somebody's got to give you those coordinates, and they show up right here in your parametric equations. Okay. So point on line is what you need. Now, so we're done with a quick review of lines in space. Now let's get the info that we're going to need for your single equation for a plane. So before I do the single equation for
Ms.
a plane.
Raskin.
Yeah.
Do you need to be recording this?
Yes, and I am recording this.
Oh, my bad. Sorry.
Yeah. Okay. Yeah. So we are going to get a single equation for a plane, but before I do that, I want to show you what a picture of a plane looks like. So it's not like an airplane. You know, an airplane would look like this. I'm not very good at drawing, but ha ha ha. Here is an airplane. That's not a plane. Okay, that's not the kind of plane we're doing. So a plane in space is like a flat, infinite surface, you know, and it's flat. I'm going to draw a portion of a plane. Here's a portion of a plane. And that's just a piece of it. It's understood to go off in all infinity directions, you know. So, and it could be at any angle. Like I could draw another one, say over here, you know, here we go. Here's another plane, you know. So there's a plane. So what are the 2 pieces of information? So one of the pieces of information should be kind of obvious. We would like to have a point P in the plane or on the plane, point on the plane. So that's nice to have. And what other piece of info are we going to require in order for us to get this equation for a plane? And this is kind of weird because it's counterintuitive unless you've seen this stuff before. It's going to turn out that you need a vector, but not a direction vector. You're going to need a vector, I'm going to call it N here, that's orthogonal, that makes a 90-degree angle with your plane. So, and they also call that a normal vector. Normal means orthogonal in this sense. A normal vector to the plane. Okay, those are the 2 pieces of info. I was like, ew, well, why do we need a normal vector? That seems weird. I'm going to do the quickie derivation so that you know where it comes from. And then after that, you'll be able to even derive it for yourself just in case you forget it. So there's a picture of a plane in space, or at least a portion of it. Great. So we have a point P that is on the plane, and we have the normal vector that's making that 90-degree angle. Now, what about Q? Q is just an arbitrary point. So Q is any point that lives on the plane that's arbitrary. So his arbitrary coordinates are X, Y, Z. Arbitrary coordinates. Now you're going to be given the fixed point P that has actual numbers X1, Y1, Z1 for that guy's coordinates. Okay. And then you got to have your normal vector N, and let's just give the normal vector N the components, just say A, B, and C. Okay, now this plane, if I'm going to describe all the infinity points that live on this plane, and there are infinity because it goes on in all directions, it consists of all arbitrary points Q with arbitrary X, Y, and Z coordinates for which the vector PQ is orthogonal to N. So I hope you could see even from this picture that when I form PQ, it is going to be orthogonal to that normal vector N. Any Q, like I could even pick Q way over here. What the heck, it doesn't matter. If I form PQ over that way, we're still going to have a 90-degree angle between the PQ vector and the normal vector. We're guaranteed that. So now, what do we know about two vectors that are orthogonal? When you take the dot product of two vectors that are orthogonal, what is the answer that you always get?
0.
Good. So that has to be true. Fabulous. So what does that mean? Well, this vector ABC dot product with, and now I'm going to form the PQ vector going terminal minus initial, and so on. So X minus X1, Y minus Y1, Z minus Z1. And you guys should remember how to take a dot product. You multiply the X components together, plus then you multiply the Y components together, plus you multiply the Z components together, and you get that whole expression equal to 0. Now, folks, this is the standard equation for a plane in space. You can fill in the rest of this theorem, and this is a very important theorem, put a star by it. So I'm going to help, you're going to finish it off. That's why you have to come to lecture. Having a vector N with components A, B, C, normal to the plane, can be represented by A, and I'm just going to copy down what I just had there. Now, Briggs is really not very good because I don't think Briggs goes over this standard equation for a plane very well. So there's kind of a big missing for me. Briggs has a lot of gaps for me as a Calculus 3 instructor. I'm not real happy with it on many occasions, and this is one. This is known as the standard equation. Sometimes on quizzes and exams, I will ask you for the standard equation. So if you give me something else, even though the answer is right, I'm going to take away points. Well, I had the answer on my paper. Well, then you didn't listen to directions. Okay. Now, if you do multiply it all out, then you'll get what's called the general equation for a plane. So what do I mean by multiply it out? Well, you take this standard equation, and you start distributing the A, the B, and the C, and then clean it all up and combine like terms and blah, blah, blah. And you're going to get AX plus BY plus CZ equals some constant, D. Okay. Now, I think Briggs, when they give you their general equation for a plane, they like everything on one side and 0 on the other. Okay, fine. So what they do is they just move the D to the left-hand side. So, it looks like mine, but, you got everything on one side and 0 on the other. But that is the general equation. Okay. Now, the standard equation is kind of nice because you can cherry pick off the normal components from the equation, and you can pick a point right off of there. Whereas if you're given a general equation, you can't immediately grab a point, although I'm going to show you it's pretty easy to do once we start graphing and sketching planes in space. But you definitely, the coefficients of the X, Y, and Z, those are, if you cherry pick them off, going to give you you can recreate your normal vector to your plane. You're guaranteed that those guys are it. Okay, so now we're going to do a classic problem. Put classic here, because if you don't know how to do this problem, you shouldn't be graduating Calc 3. Like every self-respecting Calc 3 instructor teaches you this particular problem. Okay, so what is it? here's a picture of a plane. And remember, the two pieces of information that we need to get the single equation for a plane in space is we need a point on the plane and we need a normal vector to the plane. Those are the two things we need to come up with, you know, this theorem, the equation for a plane. But I claim we don't have everything here. They gave me 3 points that are contained in the plane. Gee, that's not helpful because I only need 1 point. And they didn't give me a normal vector. So this is where it gets fun. You're going to use some previous knowledge from last week to help you complete this problem. Yeah. So I'm going to label these points P, Q, and R so I don't get confused. And I highly recommend you do the same if you're given 3 points. And you can name them whatever you want, but you know, A, B, C or whatever. P, Q, R is pretty typical. So what I'm going to do is I'm going to form the vector PQ. And you guys know how to form a vector given 2 points. And then I'm going to form another vector PR like that. And then I'm going to take the cross product of PQ with PR or PR with PQ. It doesn't even matter what order, because if you take the cross product of PQ with PR using the right-hand rule, you'll get a normal vector pointing down. On the other hand, if you take the cross product this way, PR cross PQ, you'll get a normal vector pointing up. Either way, it doesn't matter which normal vector because both of them are orthogonal to our plane. So it doesn't matter. Just get one or the other and we'll use that one. Okay. So we're going to first form, this is step 1. We're going to form PQ and PR. And then it's going to turn out that the normal vector that we want to our plane will be the cross product of PQ with PR. Okay, so I'm going to do this slowly here. PQ, if I do terminal minus initial and 0 minus 2, and then 4 minus 1, and then 1 minus 1, and I get a vector with components negative 2, 3, 0. And I'm going to do the same thing to form the vector PR. Let's see here. I'll have negative 2 minus 2, 1 minus 1, 4 minus 1, and I get the vector negative 4, 0, 3. Okay, fantastic. And then the normal vector to the plane is going to be PQ cross PR or PR cross PQ. It won't matter here because both are legitimate orthogonal vectors to the plane. And I'm going to use the 3 by 3 determinant method, and I like to see this in full excellence. So your IJK standard unit vectors are across the top, and then you put the components for the PQ there and the PR here. And then I'm going to get a 2 by 2 I hat minus 2 by 2 J hat plus 2 by 2 K hat. This is going to be 3, 0, 0, 3. This is negative 2, 0, negative 4, 3. This is going to be negative 2, 3, negative 4, 0. And you have to be careful here because some of you made arithmetic errors when you were doing some of these 2 by 2 little determinants, and that kind of blew out the whole problem. So here it's going to be 9 minus 0, which is 9 I hat. Minus, what do we have here? Negative 6 minus 0, that's just negative 6, plus 0 minus, minus 12. A lot of negatives running around there. Oops. And I'm going to write it in component form just because I like to. And I get actually all 3 of those components are positive. That's fine. Now, here's the issue. We have what we need now. We've got a normal vector to the plane. Yay. And we not only have 1 point, we have 3 points on the plane. So which one of those points, or does it matter, should I use when I'm writing up the equation for the plane here?
You can just use one.
Well, which one? Should I use P
Use
or
any.
Q or R, or does it even matter? Like if I use P and you use Q, is one of us wrong?
Well, if they're all orthogonal, it should be fine to use any of them.
Good. We should be able to use any of those points. Does that mean my answer will be different from your answer? Kind of like when we had the issue with parametric equations for a line. Remember, it turned out those weren't unique. Like your answer might be legit. My answer is legit, but they don't look at all the same numbers. No. It turns out even though the standard equation, it won't matter which point you use. Let's say you use P, I use Q. After we multiply it all out, we'll get the same exact answer. Okay, so it doesn't matter which point you pick, just pick your favorite. I'll use P. Okay, I'm just going to use the coordinates for P here. So I'm going to first take the first component from my normal vector, parentheses x minus 2, plus 6y minus 1 plus the 12, parentheses z minus 1 equals 0. This is the standard equation. And they did ask me for the general equation. How do you know? Well, I read the directions. It says general equation for a plane. So that means we need to multiply this junk out and just do a little bit of cleanup. So if I start distributing, I get 9x minus 18 plus 6y minus 6 plus 12z minus 12 equals 0. And then I'm going to keep all the variables on the left. And I am going to, let's see, negative 18 minus 6 is negative 24, minus 12 is negative 36. If I add positive 36 to both sides of the equation, I get that. Now I'm going to take away 1 point from this final answer. I won't always do that, but for this one I will. Let me go over why. Because this is the answer. It's like, hey, what's wrong with that? If you can, if possible, reduce it to lowest terms. Well, what do you mean? Well, all of the values that appear here, the coefficients of the variables as well as the constant, have a common factor. So you want to divide out by the greatest common factor, which in this case I think is just 3. So if I divide both sides of the equation by 3, you're just making it look a little prettier, that's all. You're just making it look a little bit prettier. It's the same thing. So this is the answer I want to see, your final answer, okay? And we're done. So to recap, this is a classic problem in Calc 3 where you're going to be asked to find the equation for a plane, and they give you 3 points contained in the plane. And you've got a lot of work to do. It takes a little bit of work. You got to form a couple vectors, then you got to take a cross product of those vectors, and then you got to use all your knowledge now and your standard equation for a plane, and then multiply it out and get your general equation. Okay, any questions? Okay, let's move on. Now I'm going to do a problem that I call a double whammy, but these are the kind of problems I love to put on my exams. You have to have knowledge of parametric equations for lines and an equation for a plane in space just to do one of these problems. And sometimes they're really fun, I think. So let's take a look and figure out how to walk through these. And that's going to see what's going on here. So they want the general equation for a plane that passes through the point. Oh, good. They gave us a point on the plane. You know, here, let's say I'm drawing a picture. Oops. Here's my plane. There's a point P that lives on the plane. Fine. And they're saying that the plane has a normal line, that means orthog, that is normal to the plane. So there's a line, I'll just draw some line here, that, you know, it pierces the not necessarily through P. It may be far away. Like I could put P way over here, you know, let's say they're not even close. This line, I'll call it L, is making a 90-degree angle with the plane as it punctures the plane. That's all you're given. Finish the problem out. Well, hells, bells, they didn't give me the normal vector. Yeah, but if you cherry pick the direction vector for the line, which is, you know, parallel to the line here, this red vector here, I'll call it V. If you can give me those components, I'll have, that's automatically going to be a normal vector for my plane. Well, how do you do that? Well, remember the coefficients rather of the parameter, -5, 3, -1, you cherry pick them off of the coefficients of the parameter t. We call t the parameter. So in other words, the normal vector for our plane is going to have components -5, 3, -1. And so now your standard equation of your plane, EQN is short for equation, is going to be the first component of your normal vector, x, minus the x coordinate of your point, plus the y component of your normal vector times parentheses y minus the y coordinate of your point, plus -1 times parentheses z minus 7, that's a z right there, equals 0. So there you go, there's standard equation, fine. But I won't give you full credit because it says general equation. Oh, okay, so that means we got to multiply everything out. -5x, don't forget to multiply a negative times a negative is a positive. Yeah. Okay, what else do we have here? That's going to be a minus c plus a 7. And then if I keep all the variables on one side and move all the other stuff to the other side. Okay, what do I have here? Oops, this is supposed to be a 20, my bad. I can't multiply. Let's see here. So we have 20 plus 3 plus 7, that's 30. And then we'll subtract 30 from both sides. I get negative 30. Now, once again, I'm going to take away points here. And you're going to go, what? All of these numbers are relatively prime. And I'm going to go, yeah, but I'm still going to take away -1 point. Wow, you're really hardcore. Well, here's why. Notice how we have more negatives. Oops, that's a negative, and that's a negative than positives. You just want to make it look pretty. Well, really? Yeah, that counts. So multiply both sides of the equation by -1 just to have less negatives running around. It's still equivalent, okay? It just looks nicer. That's all. Less negatives is not as harsh on the eyes. Okay, I don't make this stuff up, people. I report it. If you think it's me being strict, trust me, there are books that have that too. Okay, questions on that one? That was a double whammy.
I had a question. How are we getting 30?
Okay, when I distribute -5 times -4, I got 20.
Yeah.
Plus 3 plus 7.
Oh, okay.
I'm just adding up all the constants, yeah. And then when I move that to the other side, I subtract 30 from both sides. Is that okay?
Yeah, thank you.
You're welcome. Any other questions? Okay, so now we're going to figure out something kind of cool. Briggs doesn't focus too much on this, but I do. So I put, you'll see, it's in your homework. What if you wanted to find the angle between two planes? You know, they're intersecting. And so here's a plane right here, or at least a portion of it. And then this pink plane is also there. And then this angle between them, we'll call it theta. What if you want to find that angle? That's kind of cool. Now, you have to be careful because I want to point something out because it's going to come up in the equation. If I extend the blue plane a little bit, you know, he actually keeps going forever and ever in all directions. And I extend the pink plane a little bit. Whoops, that wasn't pink. Sorry. Colorblind today. Extend the pink plane. Woo. Can you see that, you know, where these lines, where the planes intersect is a line? By the way, this is called the line of intersection. It's kind of like the binding of a book. But what I want you to notice, if you can imagine, there's another angle here on the other side. I'll call that alpha. Do you see that alpha is also an angle between the two planes? That's not the angle we want. We want the angle that's acute. So this theta is there for a reason. We want the acute angle, the angle between 0 and 90, not the one on the back side here, which is clearly larger than 90 degrees, okay? So how do we make sure we get the acute and not the obtuse? I'll show you in a second. But first, do you recall that the angle between two vectors is given by the following formula? In fact, you just had it on your quiz, so hopefully you remember it. If you're trying to find the angle between two vectors, first you find the cosine of the angle, and then you take cos inverse of both sides. Does everybody remember this lovely formula?
Yes.
Good, because that's going to help us get the angle between two planes. Really? Yeah, well, you need vectors to do it. So what you're going to do is you're going to grab the normal vector to one of the planes. This n1 is the normal vector to the blue plane. And then the n2 is a normal vector to the pink plane. And what you'll do is you'll find the angle between the normal vectors. So the claim is the angle between the planes. Here's the claim I'm making. The angle between the planes, which is theta, is the same as the angle between their normal vectors, their respective normal vectors. And that's kind of cool, I think. And if you understand that, you're well on your way to understanding some other stuff that's kind of hardcore. Okay? So then what? So you're going to go, well, cos of the angle between the planes is going to be n1 dotted with n2 all over the magnitude of n1 times the magnitude of n2. And then we're going to add some little extra here. So this is going to be the extra I'm going to add to the formula. we're going to want to, and this is to make sure that this cosine, you want to stay in quadrant 1. So the cosine has to be positive, so you get angles that are less than 90. So, or if they're equal, then that means the planes make a 90-degree angle. So you got to put absolute value bars here. Now, please don't put absolute value bars anytime you find the angle between two vectors. Okay, that's not okay. Like this original formula I gave you in the first week of class, that's still legit. Don't start going, well, I'm going to put bars over here because she said so. And I'm going to go minus 1,000,000 points. I never said that. If you're just finding the angle between two vectors, you certainly use this formula and you don't need the bars because it could be your cosine is negative. However, when you're using it to find the angle between planes, to ensure the acute angle, you put the absolute value in there. That's all. Now, so how do you, so to answer the question, how do you make sure you get an acute angle and not the obtuse angle? You take the absolute value of the dot product, okay, of N1 and N2. That's all. Okay, now, how do you know if two planes are perpendicular to each other? Well, when they intersect, they make a 90-degree angle. Yes, and that would mean that the dot product of the two normal vectors would equal what? When you got 90 degrees, what are your dot
0.
product? Yeah. And they're parallel if one of the normal vectors is a scalar multiple of each other, or if you take the cross product of those two, you would get 0. And some of you use that to prove that one problem on a quiz, and this had nothing to do with it. You said, well, that's true if the cross product is 0, or the 0 vector, I should say, not 0. And it's like, no, it's true all the time. Okay, now let's do one example where we find the angle between two planes. Fine. So here's a plane, there's a plane, go get the angle between two planes. Great. And then we'll do it in degrees and we'll round to the nearest hundredth of a degree. Fine. So first you got to get the two normal vectors. And I claim you're going to cherry pick the normal vectors right off of the equation for the plane. What do you mean cherry pick? Well, the normal vector to this first plane is just going to be the coefficients 1, -2, 1 that you see on the variables x, y, and z respectively. And then the normal vector to the second plane will have components 2, 3, -2. That's always going to happen. So then what? Well, we're going to use the formula cos theta, the angle between two planes, is going to be the absolute value of the dot product of those normal vectors divided by the product of their magnitudes. Fine. And just to remind myself to take absolute value, I'll start. So you're going to go 1 times 2 plus -2 times 3 plus 1 times -2. You guys should know how to do a dot product, right? And you're going to divide that by the square root times another square root. So this is going to be 1 squared plus 2 squared plus 1 squared. This guy will be the square root of 2 squared plus 3 squared plus 2 squared. And it turns out I'm going to get on the numerator the absolute value of the dot product, which is a -6. Down here, I get square root of 6, square root of 17. And you know the drill. So if this is cos, my theta is going to be inverse cos of 6 all over the square root of 6 times 17, which is the same as cos inverse of 6 over square root of 102. And I get approximately 53.55 degrees. And that's the angle between those two planes. Okay, questions on this one?
Just finishing on writing it up.
Okay, so part B of this problem is going to knock your socks off. I love it. Hint, hint, you're going to see it on a future quiz and exam because I really love this kind of problem. Yeah. I love it. It's classic. It's a classic Calc 3 problem. What is it? Well, find the parametric equations for the line of intersection. What are they talking about? Well, if you go back to the picture of the two planes intersecting, that's over here. Boy, did I make a mess of that. If you look at where these two planes were intersecting, because two planes are either going to intersect or they're not. and that means they're parallel if they don't. This line right here, which does go off in infinity directions because the planes are infinite, that is the line of intersection. And it's a nice line. And our job is to try and find the parametric equations for that line. Ooh, this is a little bit tricky. So try to follow me with the strategy. There's a couple different ways to do this problem. If you are taking linear algebra, you could solve the system of 2 equations and 3 unknowns. And then you'll end up with infinity solutions because there are infinity points that live on that line. And when I teach linear algebra, I call it parameterizing because that's essentially what we're going to be doing is parameterizing it because we have to come up with the parametric equations for that line of intersection. So that's one way to do this problem. There's another way to do this problem, the Calc 3 way. So I want you to do it that way. Okay, if you're taking linear, fantastic. Know how to do that, and we're going to do it this way. Okay, because I want to use some Calc 3 techniques. It's going to turn out, you guys hopefully remember that to get the parametric equations for a line, you need 2 pieces of info. You need one, a point that lives on the line. That's going to be the hard part for this problem. So we're going to wait to do that. And the other thing you're going to need is a direction vector for the line. A direction that a vector means that it's parallel to the line. So here's my claim. If I take the cross product of these 2 vectors, I will get a vector. So in other words, n1 cross n2, I will get a vector that's orthogonal to both of those 2 originals, kind of lying on its side. And this vector, I hope you can see, is definitely parallel to the line of intersection. So that's my claim. So the claim here is the direction vector for the line is V, and it will just simply be obtained by taking the cross product of the 2 normal vectors of those 2 planes. Doesn't matter what order because it'll be pointing in the opposite direction. We don't care. It's still parallel. Okay, so let's go do this. So I think I already told you that you first cherry pick off the components of those normal vectors, and we already did that in the previous problem. So we already got those babies ready to go. And so now if we get the cross product, so we're just going to go n1 cross n2, I hat, j hat, k hat, 1, -2, 1, 2, 3, -2. And you're going to go like this. I'm going to do this really fast. Woo! Try to keep up. Yikes. Yikes. That's a -2. Boy, that looks pretty bad. And after you do your little 2 by 2 determinants, I claim you get, what the heck do you get? Oh my goodness. I get 4 minus 3 is 1, -2 minus 2 is -4, but then you have to take the opposite of that. So that's +4, and then 3 minus a -4 is 7. Okay, it's 147. Great. But here's the problem. How do you get a point that lives on the line? And this is a little bit tricky. Because the point has to be a point that lives on both of the planes. Like it can't just be, well, I'll find a point on one of the planes. Like, oh, I'll just get this point over here on this plane. No, that's not on the line. Well, I'll get a point on the other plane. No, you need to get what you have infinity choices here, but it has to be a point that lives on the line of intersection. Now, if you already took a linear class, so let me allude to linear right now, because this is how you would solve this whole problem in linear. Oh, come on, Microsoft Surface Pro, don't do this to me now. Stop, please. Don't leave me alone. You're solving this system. You're like taking this plane equation, which is a linear equation, and you are, this is a system of equations. It's 2 equations and 3 unknowns. And in linear, they teach you how to solve this. And it turns out when you have 2 equations and 3 unknowns, one of 2 things can happen. You can get infinity solutions or no solutions. You won't ever get like a single answer. Okay. You can get a single answer if you have 3 equations and 3 unknowns, and it's all nice. I don't want to get into it. So what can we do here? So what I'm going to do is I'm not going to do the linear way, but I will say, if you're a linear person, you know this. If on the right-hand side of your linear equations, you have all zeros, which we do here, this is known as a homogeneous system. It's homogeneous if the constants over here are 0. And that means that the point 0, 0, 0, which is called the trivial solution, is a solution. You're guaranteed that. Now, if even one of these constants over here isn't a 0, you're not guaranteed of that. Now, what's another way you could get this answer if you didn't take a linear class and you had no idea what a homogeneous system is, and you're like, what? The quick and dirty way is you force one of the coordinates to be 0. So here's the other way to get at your point. Let's say you force z to equal 0. And so you're going to have a system of equations now where you kill off the z's. So now you have your system, because you forced the z to be 0, looking like this. And this is a baby system of equations that I'm hoping you can easily solve from your beginning algebra days. And then you can get, and this actually does have a solution. You'll get x equals 0 and y equals 0. And then you already said that z equals 0, aha, because you force z to be equal to 0. So aha, now you have a point on the line. And then you finish up the problem. You have x, y, and z equals, and you know your point is 0, 0, 0, although you don't have to write it. I'm just sort of doing it to sort of make a point here. And so when you give me your final answer, I don't want to see the 0 plus, because it's like, okay, you know. So then we can just kill that off and we're done. So final answer, the parametric equations for your line of intersection looks like that. So I don't have time to do example 6, but I do want to say for those of you who are courageous and you want to do it on your own, let's see if I have the answer somewhere. I don't know if I put it somewhere. What did I do? I don't know where I put it. 4, 5, 6. Oh, so this one, you know, you're going to take 1, 2, 1, and you're going to take the cross product of that with 2, 1, -1, and that's going to give you a direction vector for your line of intersection. These are not multiples of each other. So that means that this means the planes do in fact intersect. Therefore, the planes are not parallel, and they do intersect. Otherwise, you'd be wasting your time trying to find the line of intersection. They have a line of intersection. You don't want to waste valuable time. So then what? After you take their dot product, cross product, what do you get? I get your vector is -3, 3, -3. And then what? How do you get a point that lives on the line? Because this one's harder. So you again force the z to be 0 in both equations, and you solve this cute little system of equations, which is, you know, baby algebra. Yay. And so your point, which you know has a 0 z coordinate because you forced it, is, looking around here, I get, what do I get? Oh, I get something nice. I get 3, 5. Is that what I did? Yeah. So I got, no, y was 1. Sorry. Y was 1. And so this is the point. And so then you use these two pieces of information to get your parametric equations for your line. So I'll let you kind of work on all that, but I just walked you through it. Now, the linear algebra way would have been to solve the system of equations from scratch. You know, you've got 3 equations and 3 unknowns. Go do it. Okay. So now we're done with that. Woohoo! And we're ready to sketch planes in space. Now, I usually don't want to make you be a graphic artist because, look, I'm not that good either. That's why I'm not, you know, I didn't major in graphic art. In fact, I'm pretty lame when it comes to trying to draw anything. But I've gotten a little better over the years because, you know, I got to teach this class. I got to be able to draw some things in 3D and not look too weird. So here's the deal. When you're sketching planes in space, and I'm going to require this in my class, the key is if a plane intersects one or more of the coordinate planes, and remember you have 3 coordinate planes. You got the XY plane. If I draw a picture here, there's x-axis, y-axis, z-axis. The XY plane is that guy there. The second coordinate plane you have is the YZ plane. Where's that guy? That'd be this guy here, like that. And then the last and third coordinate plane that you have to worry about is the XZ plane, and that's this puppy right here. If your plane that you're trying to do business intersects one of those standard planes, if you will, we call the line of intersection the trace of the plane in the given coordinate plane. And this is an important word because when we look at other surfaces on Friday, we're going to look at like cylindrical surfaces and quadric surfaces and have some fun. It is going to be important if you're going to sketch one of those babies that you know what it means to have a trace as it cuts through one of these three coordinate planes. Okay, so the trace is some kind of curve, and the curve for us is just going to be a straight line because planes don't make curvy things. Okay, so to sketch a plane in space, we do what? And you're going to fill in the blank here. I got to get rid of this because I made too much of a mess. You're going to make it easier for yourself. You're going to find the points of intersection with coordinate axes, if any, and its traces in the coordinate planes. You kind of have to worry about all of that to draw a plane in space. So this is just thinking in 3D and trying to sketch a plane in 3D. And we're only going to sketch a portion of the plane because remember, planes go off in infinity directions. It's like an infinity thin film that's flat. So I want to sketch 3 planes. Well, how come 3? That's kind of overkill. No, because all 3 of them are slightly different from each other, but they're all legitimate plane equations. So I want you to look at these 3 equations. This one probably looks similar to the ones that we just did when we were finding, you know, find the equation of a plane, you know, whatever, when we got an answer. Where the hell did we get one of these answers? You know, like this one. It's like, oh, that looks familiar. It's got the X and the Y and the Z in there and everybody's happy. But you may not be guaranteed of having all of the variables there. You may have a missing variable or 2, and it's still a totally legit plane. Well, how do you tell if it's a plane? Because it's what we call a linear equation. All of the variables are only raised to the 1 power. So like that's X to the 1, Z to the 1. Okay, that's a legit plane equation. Here it's Y to the 1. Yeah, but there's no X and there's no Z in that last equation. I know, I don't care. It's still a linear equation, which means it represents a plane in space. Now, when we start having exponents on that, like we will on Friday, like if we have 2x squared plus z squared equals 1, this is not a plane. But it is a surface. So it is a surface. It's just not a flat surface. Okay, so I want you to be able to recognize the difference. You got to be a smart rat when you're playing the game of Calc 3, because we're going to be dealing with all kinds of surfaces for the rest of the semester. And I want your eyeballs to be easily focused on what is a plane equation. It's when you've got your variables 1 or 2 or 3, and they're all raised to the first power only. If even one of them isn't, then it's representing some other kind of surface. Okay, so how do you sketch these puppies? This is the fun part of today's lecture. All right, this is where you don't have to think too hard. All right, so it's like, okay, well, first get your X, Y, and Z axes up here. There we go. And then you're going to find intercepts. So how do you find the X intercept? Well, you force the Y and the Z coordinates to be 0 and plug in zeros in the equation. And so you'll just get 3x equals 12, and then divide both sides by 3, and your X is equal to 4. So the point 400 is a point that lives on your plane. Okay, so you're going to go and find 400, which is right there on the X-axis. And then you're going to go, all right, well, let's go get the Y-intercept. How do I get a Y-intercept? No problem. You're going to set X and Z, force it to equal 0 in this plane equation over here, and then you'll just end up with 2y equals 12 or y equals 6. And so the point 060, 1, 2, 3, 4, 5, 6, there we go, 6, that point right there is a point on your plane. And then finally, go get the Z-intercept. Okay, how do you get that? No problem. Force the X and Y coordinates to be 0 in your plane equation, and then I get 4z equals 12, z equals 3. So the point 003, 1, 2, 3, is going to be a point on my plane. Now, you get the traces. Like the trace, as this plane cuts through the YZ plane, the trace is that line. That's a trace. As the plane cuts through the XY plane, it makes this straight line as it cuts through that coordinate plane. And then the trace as it cuts through the XZ plane is that straight line. And then this triangular portion, I'll just color it in, is a portion of the plane that we're basically graphing. Pretty easy, huh? Let's do another example. How about this second equation? It's missing the y. I know, don't worry. What that's going to mean in this case is this guy is parallel to the y-axis. It has no y-intercepts. No y-intercepts. Really? Yeah, it just doesn't. So you're still going to do a similar process. So go get the x-intercept, and you'll do that easily by setting z equal to 0. And that means the x-intercept will be half 0, 0. And so if you're trying to graph this puppy, got your coordinate axes, you know, here's 1, but you want to graph a half. Okay, right there. That's about halfway through. And then to get the z-intercept, no problem. You're going to force the x coordinate to be 0, and then I just get z equals 1. So the point 0, 0, 1 is a point on your plane. And this is the part where students choke. They go, oh, I don't know what to do. I'll just draw a straight line. There's a plane. No, that's a line. That's actually the line that is the trace as this plane cuts through this XZ plane over here. That's not the plane itself. And this is the hard part where you have to think in 3D. What do you mean? I need to extend this trace out. And here is the portion of the plane. That is a plane. Okay, so you have to kind of think a little bit to draw that one. And it is kind of tilted a little bit, and the y-axis is behind the plane there, the way it's facing us. So it's a little bit weird. Okay, finally, here's a plane that's missing 2 out of the 3 variables, yeah? And it's kind of obvious. What do you think the y-intercept is? Any guesses?
3.
Yay, us! Success. So in other words, it better be 030 better be contained in the plane. Otherwise, we got problems. You're like, okay, there it is. Oh, I know, the plane is just a dot. No. It turns out that this is going to be a plane that's parallel to the XZ coordinate plane. It's parallel to that because, you know, it doesn't even have any X or Z intercepts. And this is where it gets really tough to draw in 3D. So please forgive me if I draw something that's a little weird and confusing, but I'm going to try to draw a plane that's vertical to the XZ plane. It's like sitting straight up and parallel to this XZ plane over here, and only has a y-intercept, no X or Z intercepts. And there you go. There's the plane. Looking good. Okay, I got 20 minutes to go and I'm going to use it. I'm sorry. Whoop. All right, now let's talk about distances. Now, when you're finding distances between points, planes, and lines and all this jazz, you really are, this is like the part that should be exciting for you. Like, especially if you're an engineer or if you're a computer scientist who wants to get into video gaming. This right here is like your wheelhouse. Okay, I'm talking to you because this is relevant. Oh, really? I don't care. Well, okay, fine. You don't have to care. But I think it's exciting because you're getting distances in 3D. And, you know, we only learned how to find distance between 2 points in 3D.
I was ready to skip it.
You guys talking to me? Mute you. Okay, so let's do a quick review. What's one distance you already know how to get in 3D? I'll give you a hint. You know how to find the distance between 2 points in 3D. Does everybody remember that, or maybe not? Because if you don't, the rest of this course is going to be kind of not fun, because that's like one of the key distance formulas that I taught you in this class. Like it's going to show up on a quiz or a midterm.
That's x2 minus x1 under the square root with y2 minus y1.
Squared.
Yeah, squared. My bad.
Yeah, you're on the right track. All right, Nathaniel, congratulations. You win. What's behind door number 3? The Bendix washer dryer. Okay, so you already know a distance formula in 3D. It's the distance between 2 points. Great. But now we're gonna jack it up a notch. Okay, what do you mean? We're gonna find the distance between a point and a plane. That's key. And then the distance between a point and a line. Now, when I say distance, folks, please know that it's understood to be the shortest distance, not whatever distance you think, because I had a student last year who, I don't know if it was a quiz or exam, God bless him. He gave me a distance and he goes, well, it's a distance and you didn't say the shortest distance. And I went, okay. It's understood when you're even learning about the distance between a point and a plane or a point and a line that it is the shortest distance. Otherwise, there's infinity answers, and I'll show you what I mean. So what if you were being asked to find the distance D between a point Q, there's the point Q, and this plane here, okay? Now, you want the shortest distance, not, oh, I'll just take any distance, you know, well, this works for me. No, if you drop a perpendicular down from the point Q to your plane, there's a perpendicular 90-degree angle. This is your D, your distance. I don't want you finding, well, I'll just find this distance over here. That's good enough for me. No, because that is not the shortest distance and it matters. Okay, so please. All right. So how do you get that distance there? Like not just any old distance that your heart desires. This is interesting because as long as you have a point P that is contained in the plane, or you can get one, you form the vector PQ. Please do not give me the magnitude of that as the distance because it ain't. It's not the shortest distance between Q and the plane. But you're going to project this vector onto the normal vector. So this distance D is going to be the magnitude of the projection of PQ onto the normal vector N. And they give you all this information here, where P is a point on the plane. Okay, so don't use this formula because I'm going to take that as and then derive it. So the distance is the magnitude of the projection of PQ onto N, but you're not going to do all that. I'm going to give you the shortcut. So I'm going to do all the hard, heavy lifting for you. So you're like, oh man, this looks horrible. But then you're going to use some of your knowledge. You're going to go, hey, what happens when you project PQ onto N? How do you get it? Well, it's a scalar times a vector, where the scalar is the dot product of the two vectors divided by the magnitude of the vector you're projecting onto, that would be N, magnitude squared, times the vector N. And then when you take a magnitude of a vector, you get a magnitude, and the magnitude of a dot product is just absolute value. It just forces it to be some positive scalar. And the magnitude of a magnitude is still the magnitude. And so this becomes magnitude. And then you reduce this to lowest terms. Does anybody see anything that cancels here for me?
The ends.
The N.
Yeah, the magnitude of ends, and you're done. And so anytime on a quiz or an exam, if I ask you to find the distance between a point and a plane, you can use this quick and dirty formula right there, baby. And you're done. Now, the hard part of these problems, and this is the struggling point when I see students choke on these problems, is they a lot of times will not give you the point P that lives on the plane, that's contained in the plane. Well, how do you get it? Well, you can easily find an x-intercept, and that'll be a point that's contained in the plane, or if it's easier, a y-intercept, or if you prefer a z-intercept, whichever one of those three works for you. That's the quick and dirty way to get your P. Pick one of those puppies, okay? Because usually they're not going to give you that. All right, so let's do an example. It's very typical. You'll see it in your homework. You'll see it on a quiz or exam. Okay, I promise. I'm just going to change the numbers. Okay, so they're giving you a point Q. So, and then they're giving you an equation for the plane. So Q is like way over here. We don't know. If you drop a perpendicular down to the plane, this is the distance they want you to get. Okay, well, how do you get it? You first have to get a point that lives on the plane, you know, your favorite point. So step one is recommended. So to get a point P contained in the plane, get an intercept. So what is the easiest intercept to get here? I'm going to get an x-intercept. What the hell? That looks pretty easy. Why? Because if I set y and z simultaneously equal to 0 in this plane equation, I'll get 3x is equal to 6, and then I can easily solve for my x. So the point 200 is going to be my point P. There he is. Yay, 200. And they gave me the q coordinates. Fabulous. Then what? Step 2 is going to be form the vector PQ. You have enough information to go do that. So for me, PQ, terminal minus initial 1 minus 2, comma 5 minus 0, comma negative 4 minus 0, equals, what do I got? Negative 1, 5, negative 4. And now step 3 is get n, the normal vector to the plane. Remember, you can cherry pick that off of your plane equation. Remember, here's your plane equation. You're going to cherry pick the components of your normal vector by simply stealing the coefficients of your variables. So 3, negative 1, 2, there he is. And now you're all set for step 4. You have all your ingredients, and your distance is going to be the absolute value of the PQ with, or N with PQ. It doesn't matter what order, because dot product doesn't care. And you'll divide that by the magnitude of n. So you're going to go absolute value of 3 times negative 1 plus negative 1 times 5 plus 2 times negative 4, whatever that is, all over the square root of the n magnitudes. You'll have the square root of, I'm running out of room, 3 squared plus 1 squared plus 2 squared. What the heck? And what do I get here? I get negative 3 minus 5 minus 8. Ooh, absolute value of negative 16. Make sure you never give me a negative number. Well, that's why you need that absolute value. If you go, well, the distance is negative 24, I'm going to go, you can't have negative distances. Okay. And so this is going to be, the exact answer is 16 over square root of 14. And if they ask me for the approximate answer, I would whip out a calculator and give them a decimal result. It's about 4.28. Okay, and I have the answer on the next page. There you go. Okay, any questions on that? Very formulaic. Everybody okay? No? I'll check the chat.
Yeah, okay.
Okay, what do you got? I'm waiting. What's your question?
Oh, I meant we're good, sorry.
Okay, so what if somebody gave you 2 planes? They either intersect or they're parallel. And in this problem, they're saying, hey, we'll prove they're parallel. So there's a couple ways to do that. If you get the normal vector for the first plane, remember, just cherry pick it off. It's the coefficients of your variables. And you cherry pick off the normal vector to the other plane. Can you tell that they are multiples of each other? Can you see that just by inspection that N2 looks like it's going to be twice N1? Sure, I'll take them. Does everybody see this?
Yeah.
Okay,
Yes.
so that's proof right there. You know, that's good enough. Or another way to prove it, if you wanted to be sweet and cute, you could do the cross product and show that you get the 0 vector. That would be good enough to me to prove the planes are indeed parallel. Okay?
Here you go.
Okay, thank you. Say hi to Zeke. Now let's find the shortest distance between the 2 planes. I don't have time to do all of this in massive detail, but I'll just walk you through it. Here's a plane and here's a plane. They're definitely parallel. You want to get a point P on this plane and a point Q on the other plane. I don't care where, you know, you already have like an N1 and an N2, and you know that they're parallel to each other because they're scalar multiples. So how would you get the point P or the, you know, whatever? The point P for the first guy, if you get his x-intercept, that's probably the easiest way to do it. It looks like it's going to be 200. This guy, you could get an x-intercept, but then you're going to get a fraction. And I hate fractions. That sucks. You know, but it still would work. You'd still get the same answer. Be quiet, Zeke. So what I did for the second plane, and, you know, if you don't like it, that's fine. I got his y-intercept instead, just so I would get, and I'll call that Q. That ended up being 0, 2, 0. And then the next thing I did is I formed PQ. And then when I use my distance formula, which one of the ends should I use? And it turns out whichever one you want, because you'll still get the same result. So after you do all this, you should get that answer. Okay, now let's do the hard distance. This is the one that can drive you nuts. The distance between a point and a line is a little bit trickier because the answer is, I'm just going to give you the answer here. You're going to, here's your line. You have a point P on the line, a point Q not on the line. The shortest distance is if you drop a perpendicular from the point to the line. There's your D right there. So you're going to take the cross product of PQ, so you're going to have to form PQ first, with the direction vector for the line. So let's just say the direction vector for the line is U. Okay, you're driving me nuts. Why don't you sit over here? So U is going to be, you know, some vector that's parallel to the line. Okay, so sometimes birds can drive you nuts. Okay. So please keep in mind, this is the shortest distance. So, you know, when I was trying to explain to the student last semester, a picture would be, let's say this is the coastline, you know, of some, you know, maybe San Diego here, and here's a ship out to sea, okay? If somebody said, what's the distance between this coastline and the ship, you know, the sailors on the ship wouldn't go, oh, land ahoy, we're like, you know, 1,000,000 miles away from land, because, you know, they're measuring this distance here. No, they wouldn't do that. Of course not. They would do the shortest distance between the ship and the coastline. And that's why, please, anytime I ask you for the distance between a point and a line, it's understood to be the shortest distance, okay? Now, how would I prove this? This is a little bit tricky to prove this, but if here's a line, here's a point P on the line, here's a point Q not on the line, what is this distance D equal to? What the heck? So it turns out if you form the vector PQ and you have a U that's going to be a direction vector for the line, if I drop a perpendicular down from Q to the line, and then I have some angle here, I don't need to figure out the angle, but I know that sine theta is equal to opposite over hypotenuse. I use that from trig. So sine theta here will be, the opposite is the D that I want, and then the hypotenuse of my triangle happens to be the magnitude of the PQ vector. Okay, fine, so what? So if I solve this for D, D is sine of the angle between the PQ and the line, or the direction vector even, and multiply that by the magnitude of PQ. And this is the part of the proof that gets like, oh man, that's a trick. And sometimes proofs involves tricks. By the way, there is another way to find the distance between a point and a line using projections. If you want to come see me in office hours, I'll show you how to do it. It's actually kind of cool. I had a student who almost figured it out in the middle of a quiz, but he ran out of time because he totally forgot this formula. It was a face-to-face quiz. So the special version of 1 is going to be, and you're going to go, oh man, you just pulled that out of your hat. And I'm going to go, yep, I did. It's the magnitude of the direction vector divided by itself. Oh, well, how is that going to be helpful? You'll see in a moment. This numerator, if you recall from a theorem, is the same as the magnitude of the cross product of those two vectors. Okay, and there is the formula you're going to use for distance between a line and a point. Okay, so here's an actual example with numbers. Okay, so find the distance between that point Q and this line. Okay, fine. So what I do first is I get a point P on the line, because you need to, and I cherry pick it right off of the parametric equations. Well, what do you mean? Be careful, don't blow this. It's the numbers that are not coefficients of your parameter. Remember, if you cherry pick the coefficients of your parameter T, that gives you the direction vector for your line. We'll do that in a second, but point P has coordinates -2, 0, and 1. The direction vector for the line has components 3, -2, 4. That's where you cherry pick your components off of the parametric equations. And now you have to go get a cross product. And you know, that always takes time because it's, you know, tedious. So you're going to go, well, oh, first you got to go PQ. Let's get PQ. Let's see, 3 minus a minus 2. What else? -1 minus 0, 4 minus 1. Okay. So those components are what? 5, -1, 3. Now you can go, okay, what's PQ cross U? And you use your determinant method. And I'm just going to cut to it because I'm running short on time. I get 2, -11, -7 for the components. And now you can get your distance from your point Q to your line. You're going to take a magnitude all over a magnitude. Really? Yeah. So you're going to go square root of 2 squared plus 11 squared plus 7 squared all over the square root of your direction vector. Your magnitude of your direction vector, square root of 3 squared plus 2 squared plus 4 squared. Okay, I get square root, some weird square roots. It turns out, now normally you wouldn't think about doing this, but it turns out I'm going to use a law of radicals. It says quotient of radicals give me the radical of quotient. It turns out that the 29 goes into 174 evenly. Who knew? Turns out it's just 6. And we reduce, and we're done. Okay, so there is your distance between a point and a line. It's pretty involved. Point in a plane is easier, but there you go. So I'm going to do a couple of the problems over here, although I did give you a bunch of hard problems. So I need you to know how to do these. I don't have time to finish it out, but good news. I did these for you. And let me just check your Canvas real quick here. What we have here. Here's Math 252. Modules. Let's see what we got here. I put all kinds of weird stuff here on your Canvas. It's up to you to go look at it. Whoa, what happened? Okay, here's standard form, equation of a plane example. Here's how you find distances, example of a distance between point and plane. Okay, so here's where, see where it says things to know, lines and planes and space extra? If you click on that, I gave you a gift. What kind of gift? Well, my gift to you. What I did is all these problems that are hard, I posted for you. What do you mean? Well, like these are all sorts of problems that I love to put on quizzes and exams, hint, hint, you know, that are kind of tricky, you know, like the first one we already did in class, like find the, and this is just your lecture notes where I filled it in for you. So I'm just, you look at this. This one is the plane that has the point 1, 2, 3, but it's parallel to the YZ plane. Well, the normal vector, you can use I hat, and that's what we do here. And then here's another really hard problem where you're given a plane that contains 2 lines. So how do you figure out the equation for the plane if all you know is that the plane has 2 lines in it? It turns out if you take the cross product of the direction vectors, you'll get a normal vector, okay? And there's more. I give you all kinds of goodies here. This is more advanced finding equations of planes and advanced finding parametric equations of lines. All done for you here. And so it's there in my lecture notes for you. So I think that's probably a good place to quit. So that's my gift to you. And congratulations, you are now done with section 13.5. And you can go and do your homework on it in excellence, right?